Today, we're zeroing in on something that is literally hiding in plain sight. Seriously, every LED, every photodetector, and especially the cutting-edge solar panels we're going to talk about today completely rely on it, yet it almost never gets the spotlight. We're talking about substrates. And specifically, we're diving into the foundations used for the absolute bleeding edge of renewable energy, Perovskite Solar Cells. Let's get right into it. So, here is our game plan. We'll start with the optoelectrotronic canvas, move into the Perovskite balancing act, check out the rigid champions, weigh up the plastic contenders, explore some extreme alternatives, and finally, figure out how exactly we go about choosing the foundation.
All right, part 1, the optoelectronic canvas.
To get technical for just a second, a substrate is the foundational, inactive, physical base where thin layers of semiconducting materials are actually deposited and grown. But really, think of it like the canvas for a masterpiece painting. The canvas itself doesn't generate light, right? And it definitely doesn't conduct electricity. But it dictates almost everything else about the physical device. We're talking mechanical strengths, optical clarity, thermal limits during manufacturing, and ultimately the lifespan of the whole shebang.
Honestly, this quote really hits the nail on the head. Without a solid, well-chosen substrate, the active layers would just be a microscopic pile of fragile chemical dust. Wow. I mean, that really puts the high stakes into perspective, doesn't it? Because we're building these incredibly delicate, nanoscale structures, and without a strong, precisely engineered base, all of that brilliant cutting-edge chemistry basically amounts to nothing.
Moving on to part 2, the Perovskite balancing act. Look, Perovskite solar cells are basically the darlings of the modern photovoltaic world right now. Why? Because unlike those traditional, bulky silicon panels that need massive energy-guzzling foundries to make, perovskites can actually be processed from liquid inks, and at relatively low temperatures. It's a real game changer. But here's where the engineering gets super tricky. Perovskites are incredibly finicky. They degrade super fast when they're exposed to moisture, oxygen, or too much heat. So picking a substrate is this massive high-stakes bottleneck. You're constantly juggling 4 things: thermal stability, chemical resistance to some really nasty solvents, flexibility, and cost. Oh, and if you need sunlight to actually pass through the base to hit the active layer, it has to be perfectly transparent too. It's literally a giant puzzle.
Okay, section 3. Let's talk about the rigid champions. The undisputed heavyweight champion of the research lab is, without a doubt, rigid glass. Usually, it gets coated with a transparent conductive oxide, stuff like FTO or ITO, to carry the electricity out of the cell. But look at that thermal limit, over 500 degrees Celsius. That is huge. It lets engineers bake crucial electron transport layers, like titanium dioxide, at extreme temperatures to get these absolutely pristine crystal structures. Plus, glass is perfectly clear, wonderfully flat, and totally immune to harsh chemical solvents like DMF and DMSO that are used to dissolve those perovskite inks. But there's always a catch, right? The glaring issue with glass is that it's heavy, it's totally rigid, and it's incredibly brittle. If you're trying to build the futuristic solar tech we all want, stuff integrated into clothing or rolled out over massive, sweeping curved roofs, well, you simply can't wrap a rigid sheet of glass around a curved surface. It's just not going to happen. Now, before we move off rigid materials entirely, we have to talk about an amazing paradigm shift: silicon as the tandem superstar. In this setup, a traditional crystalline silicon solar cell actually acts as both the bottom solar cell and the physical substrate itself. Then, the perovskite cell is printed directly on top. So the silicon bottom absorbs the infrared light passing through, while the top perovskite layer gobbles up the visible light. It's an incredible 1-2 punch that's currently pushing theoretical efficiency limits way past 35%. Absolutely wild.
All right, on to section 4, plastic contenders. Enter PET, polyethylene terephthalate. You definitely have some of this nearby right now. It's the exact same clear, lightweight plastic used to make disposable water bottles. It's super flexible, dirt cheap, and has fantastic optical transparency. If you want to make cheap, wearable solar tech or literally print solar cells on massive high-speed machines like a newspaper press, PET is your best friend. But look at that glaring thermal limit, less than 130 degrees Celsius. If it gets hotter than that, it violently warps and melts, which means engineers have to invent entirely new, crazy complex, low-temperature or photonic curing processes just so they don't melt their own canvas.
So let's compare PET directly with its overachieving sibling, PEN, or polyethylene naphthalate. PEN has a slightly tweaked chemical backbone, and that small change gives it superior mechanical strength and, this is absolutely crucial, much better barrier properties against moisture and oxygen, which, as we know, those fragile perovskites desperately need. It also bumps the thermal limit up to a much more comfortable 150 to 180 degrees Celsius, so you can bake the cells better and get higher efficiencies. The catch? It comes with a noticeably steeper price tag. It solves a ton of problems, but you're definitely paying for the privilege.
But what if you need extreme heat and you still need the device to bend? Enter polyamide, or PI. With a thermal limit of around 350 degrees Celsius, this rugged, high-performance plastic is legendary for its heat resistance. In fact, it's heavily used in aerospace applications where devices get subjected to brutal, extreme thermal cycling up in orbit. However, and this is a massive headache for solar engineers, polyamide has a catch. Have you ever noticed that distinct yellowish amber tint on aerospace electronics or flexible cables? Yeah, that color means the plastic is actively absorbing light. And in a solar cell, that's literally the exact light you're trying to capture to generate electricity. So engineers are kind of boxed in. They either have to build an inverted, back-illuminated cell where the sun hits from the opposite side, or they have to shell out massive amounts of budget for highly specialized, colorless variants of the plastic. It's a really fascinating design trade-off.
Section 5. Extreme Alternatives. Let's step away from plastic and talk about metal foils. We're talking ultra-thin, highly flexible sheets of stainless steel, titanium, or aluminum. They are inherently conductive, insanely durable, and they laugh at massive thermal budgets over 500 degrees Celsius. They are brilliant for rugged industrial solar, like integrating power directly into a corrugated metal roof. But I bet you can guess the catch. They are exactly 0% transparent. You cannot shine light through solid metal. So you have to build the whole device in a specific configuration where the top electrode is transparent. On top of that, you have to add a smoothing planarization layer, basically a microscopic primer, to cover up tiny metallic bumps that could instantly short-circuit your ultra-thin solar cell.
And then we have what a lot of people consider the holy grail of this entire field: flexible glass, things like willow glass. Engineers have actually managed to make glass so unimaginably thin, we're talking down to 100 micrometers, that it literally bends and rolls just like plastic. It gives you the absolute hermetic sealing, perfect transparency, and extreme thermal stability of rigid glass, but with the flexibility of a polymer. It stops moisture dead in its tracks better than plastic ever could. The problem? It's all in the manufacturing. It is notoriously expensive, ridiculously tricky to handle on fast assembly lines, and if you handle it even slightly rough, it is highly prone to catastrophic cracking right at the edges.
Finally, Section 6. Choosing the foundation.
So, bringing it all together, this matrix right here is basically the landscape that every solar engineer has to navigate. It's all about what you're trying to build. Want maximum efficiency in a lab and don't care if it bends? Rigid glass is your best bet. Chasing cheap, flexible consumer wearables? You sacrifice the heat stability and go with PET. Need your solar cell to survive the blistering heat of outer space? Polyamide. Building a rugged industrial warehouse roof? Metal foil. Or are you going after absolute world record tandem efficiencies? Then you build your cells straight on top of silicon. Every single one of these substrates solves a very specific problem, but inevitably it introduces a brand new bottleneck you have to engineer your way out of. So, I'll leave you with this to ponder. As you look toward the future of renewable energy, how are you looking at these materials? Are you evaluating these substrates for a specific application, maybe building a flexible prototype in your own lab? Or are you looking at the mass manufacturing bottlenecks of just one specific type to completely revolutionize the industry? Think like a solar engineer for a minute. The foundation you choose right at the start will dictate absolutely everything that follows. Thank you so much for joining me on this explainer. Stay curious, and as always, keep exploring.